Okay, so today's lesson is functions. And what I have up on the board here is our basic definition of what a function is. So a function from one set x to another set y is a rule that assigns to each element of x precisely one element of y. All right, now this is what you would normally think of as the vertical line test for functions, if you think of it graphically. All right, so if I have, pretend that's straight. All right, so if I have something like this, let's say, all right, then there is a test I can do graphically to see if this is a function. It's called the vertical line test. I draw a vertical line anywhere on the function, it only hits one point. So what that corresponds to is the idea that, right, the function from x to y is a rule that assigns to each element x, so here's my x, exactly one y. All right, so wherever I put an x, I can trace it back to the function, and there's only one y value that it's going to hit. All right, so if you compare that to something that's clearly not a function, let's say we do this. All right, then that rule of functions doesn't hold, right? Because I can pick an x value here that I can trace back to more than one y value. Okay, so all this definition is saying is you have something that satisfies graphically this as opposed to this. All right, if I can take an x and trace it back to two different y values, then I don't have a function. Okay, and that's the rule that we're going to follow. Hang on one second here, my line is too thick. Okay, that is the rule that we are going to follow for functions. All right, now a function has an input and an output when you think of a function algebraically, right? The input is what's called the domain, the output is what's called the range. So from this definition, all right, a function from a set x to a set y, all right, our set capital X is the domain. And basically what that means is it's the set of all values that you're allowed to enter into the function for x. All right, so it's the set of all, I'll say allowed variables. I forgot a W. Even on a video, I can't spell. Let's try that again. Allowed values for x. All right, so that's the domain. It's the set of all values that I am allowed to enter into the function. The range, right, that's the capital Y set there, is the range. All right, so the range is the set of all values that you get from inputting the domain into the function. All right, so it's the set of all values you get from inputting. Okay, try again. Inputting. I'll put two T's in that. I don't know if there's two T's, but there are now. Inputting the domain. All right, so in very simple terms, the domain is the input. The range is the output. If you want to think of it in programming terms, okay. So when you're looking at a function, one of the things you're going to need to be able to do is to recognize the domain of the function, all right? Maybe not necessarily the range right away, but certainly you're going to need to know what the domain of a function is. All right, so for us, for right now, for the type of functions we're going to be looking at, which are basically polynomials, power functions, and rational functions. All right, we'll get into some other ones later on in the semester, but for right now, that's it. So when we look at the types of functions, right, a polynomial has a domain of all real numbers. All right, so I can put anything I want into the domain of a polynomial. All right, anything at all. Now, when I talk about power functions, what I'm really looking at here as far as restrictions are root functions. Okay, so root functions, some of them have restrictions and some of them don't. All right, if we have an odd root, right, odd roots have no restrictions, all real numbers. Even roots have restrictions, right? Even roots, think square root, right? What can't you put into a square root? Well, you can't put a negative number into a square root if I'm working in the real numbers. So even roots have a restriction of, all right, you can put 0 in, so I can't say positives, but I can say non-negatives, right? Non-negative numbers. So basically x greater than or equal to 0. Okay, that would be non-negative numbers. And then the third type we're going to see is rational functions. All right, rational functions will have a restriction. Well, again, think fraction. What can't I do with a fraction? Well, I can't put a 0 in the denominator of a fraction. So the restriction for rational functions is you can't have a 0 in the denominator. So the domain for a rational function are any values, any numbers, that, let's see, how can I say this easily? Let's do it this way, that don't make the denominator equal to 0. Equal to 0. All right, so in terms of the type of functions that we're going to be dealing with, I believe that is all the possible types of functions that we're going to have to look at least in the beginning of the course here. Okay. So when you look at a function, the first thing you want to look at is what is the domain of that function. So if, for example, I take the function f of x equals the square root of x plus 1. All right, if I want to know what the domain of that function is, I have to look at any parts of the function that could be restricted. All right, this is not a polynomial. All right, it is a root function. So then I have to look, is the root even or is it odd? So this is a square root function. All right, a square root is an even root. So I go back to my list here. Well, even roots have to have non-negative numbers. So I take whatever's under the square root sign, right? So for the domain, I take whatever's under the square root sign and say greater than or equal to 0. Right? Now in this case, there's nothing for me to solve. There's no inequality for me to solve. That is already x is greater than or equal to 0. So that is the domain. So when we write the domain of a function, we're either going to write it as an interval or a set. All right, so I tend to prefer sets for domain, but again, use whatever you need to, whatever the book says to do, okay? So this is going to be the set of all x, right? The set of all x such that x is greater than or equal to 0. And because the domain is a set, that's the way I like to write it. If you want it as an interval, right, well, we have the inequality notation, this interval notation. If you want to write it as an interval, you could write, again, we're including 0, and we never include infinity. Okay? All right. So let's take a look at some other functions here. What can we do? All right, how about we take a look at this. Suppose I had something a little more complicated, right? Suppose I had the function f of x equals the square root of not x squared. Well, yeah, let me leave it as x squared. I'm sorry. X squared minus 2x. All right. So again, the domain, whatever's under the square root sign, has to be greater than or equal to 0. X squared minus 2x has to be greater than or equal to 0. Okay. All right, now, unlike this problem up here, we have an issue because this is not simple, right? This is an equation. Now, we talked about these kind of equations, I think, last week. Okay, so I need to solve this inequality, which means I need to remove the inequality for a minute. I need to look at the equation, x squared minus 2x equals 0. I need to solve this for where it's equal to 0, so I'm going to factor out an x. And then this factor is going to be x equals 0. This factor is going to be 0 when x is 2, right? Because 2 minus 2 is 0, so x is 2. Right, so I need my number line 0 and 2. All right, and then I just need to check, right? So if I pick a point, let's pick a point in the middle first. So if I pick a point between 0 and 2, say I pick 1. If I put a positive 1 in here, I get 1. If I put a positive 1 in here, I get negative 1. All right, so a positive times a negative is a negative. So my function is negative in here. All right, and if I put, let's say, 3 over on this side, say I pick 3 over here, I put 3 in here, I get 3. I put 3 in here, I get 1. 3 times 1 is 3, so that's positive. So I'm positive on this side. If I take like a negative 1, let's say, on this side, and I put it in, I get negative 1 here. I put a negative 1 here, I get negative 3. A negative times a negative is a positive. All right, so we get our little sign line here. All right, and now I can see, where is this function greater than 0? Well, it's greater than 0 to the left of 0 and to the right of 2. All right, so now I can come up here and I can write my domain. It's the set of all x such that x lies to the left of 0, right? So that means x is less than 0. And, or you could put a comma, x is to the right of 2, so that is x is greater than 2. All right, so if you're going to use set notation, it's going to look like that. If you're going to use interval notation, right, to the left of x would be negative infinity to 0. And remember, we're not including 0 because it's equal to 0 there, not less than 0. Union. And then greater than 2 would be 2, but not including 2 to positive infinity. All right. So either set notation or interval notation is fine. This is not fine. Okay. Don't leave it like that. All right. One of these two would be your solution to that. If you have a rational function and you want the domain, all right, I'll go for a simple one. All right, suppose we looked at one yesterday. I think that was f of x equals x minus 1 over x plus 2. I think it was something like that. Might have been x plus 2 over x minus 1. But here's a rational function. All right, so now the question is, are there any points there where the denominator is equal to 0? All right, so I take the denominator out, and I attempt to solve it for x. So this is not a bad one to solve for x, right? Just subtract 2 from both sides, and I get x equals minus 2. All right, now this point here, x equals minus 2, is excluded, because that is a point where the denominator is equal to 0. So when I come up here to write my domain, there's a couple of different ways I can do it, but the easiest one is to say the set of all x such that x is not equal to negative 2. Now this happens to be one that's easier to write as a set. If you wanted to write this as an interval, you would have to write two intervals that exclude negative 2, right? So you would go from negative infinity up to negative 2, not including negative 2, union, and then negative 2 again, not including negative 2, to positive infinity. Again, the choice is yours which way you write it. Again, in this case, I think set notation is a little bit easier. I tend to think set notation is always a little bit easier, so. All right. Now keep in mind, not every rational function is going to have a restriction, because sometimes, all right, here, let's go this way this time. All right, if I take a function, let's call it g of x this time, g of x, and suppose it was x minus 1 over x squared plus 2, x squared plus 2. All right, well, when I take x squared plus 2 out and I try to solve it, I have an issue. Again, remember, we're working in the real numbers here. All right, this has no solution. So because this has no solution, there are no points where the denominator is 0. All right, so in this case, the domain here is indeed all real numbers. Okay. All right, so be a little careful when you're dealing with rational functions. Don't assume that the rational function is going to have a place where the denominator is not defined. You actually have to take it out, and you actually have to try and find it. If you can find it, great. If there's clearly no solution, all right, then there is no place where the denominator is 0. All right, so that's domains. All right, so let's talk about function notation for a minute. All right, when you all get to calculus and you have to start working within the framework of calculus, there are some things you're going to have to do that involve plugging unusual looking things into functions. All right, so function notation, right? When I say y equals f of x, all of these parts mean something, right? F is the name of the function. I'm calling my function f. What's inside the parentheses indicates the domain variable. So this is the domain variable. What's on the other side here is the range variable. Okay. All right, so the idea with function notation is we have a function. All right, let's get a function here. All right, let's make my function f of x equals x squared minus 2x plus 1. X squared minus 2x plus 1. All right, so notice the variable that I have over here indicating the domain variable is the same variable that's over here in the function. That makes sense. That's your domain variable. That's how you want to write your function. Now, the notation gives us a way to make replacements. So suppose I say, let's let x equal 2. All right, well, that means everywhere I see an x, I'm going to write a 2. That's a lot of 2's. All right, I probably should have picked something other than 2. We'll fix that in a minute. All right, and notice when I replace into the function, I use parentheses. Always use parentheses when you drop a number into a function. All right, if you always use parentheses when you drop a number into a function, you will eliminate any possible mistakes that can be gotten from signs. All right, and I'll see in a minute. We'll take a look at it. I'll drop a negative number in and you'll see what I mean. All right, so once I've done that, then what I have over here is an arithmetic problem that I can work out, right? So 2 squared is 4. 2 times 2 is 4. Yeah, 2 was a bad number to pick. Plus 1. So 4 minus 4 is 0. So that whole thing is equal to 1. All right, so we would say f of 2 is equal to 1. All right, and that's back to our function notation up here. So what this does is it gives us a coordinate point, right? When x is 2, y is 1. So this, over here, f of 2 is 1, is another way of saying the point 2 comma 1. All right, so all these notations are equivalent. Now the reason that I'm worried about the parentheses here, let's do this. Let's let x equal negative 3. All right, so everywhere I see an x, I'm going to replace with a negative 3. All right, and here the reason for the parentheses become clear, right? I'm squaring negative 3, so I need to have that inside parentheses. All right, so that becomes 9. Minus times minus is plus, so that becomes plus 6, plus 1. So that's 15, 16. All right, so that's equal to 16. All right, so what we get out of this is f of negative 3 is 16. So that is the point, negative 3, comma, 16. So I've just found 2 points that lie on this curve. All right. Now again, what you put in can look like anything at all. Suppose I want to let x equal the square root of 5. All right, then I'm taking f of the square root of 5. Which means I'm going to replace everything over here now with the square root of 5. All right, so the square root of 5 squared is going to be 5. Minus, now what do I do here? Well, there's nothing I can do there. That's just 2 square roots of 5, right? 2 square roots of 5 plus 1. All right, now I want to combine like terms here, right? So I've got 5 plus 1 is 6. So I get 6 minus 2 square roots of 5. Right? Now, I hear a lot of you yelling at me in my head. Can I just go to my calculator and get a decimal for this? Well, that's going to depend on what you're doing. All right, like we talked about the other day, if you're in one of your engineering classes and you're asked to solve a problem that gives you an answer that looks like this, all right, you're probably not going to leave it that way because you're going to probably have a tolerance within which you need your answer. So that's going to mean turning it to a decimal and to however many decimal places you need. As far as mathematically, for right now, I would just leave it like that, all right? If we need to do something with it, we can turn it to a decimal later, okay? All right, but if I want a coordinate point on my graph, I'm going to have to turn that to a decimal. All right, so I'm just going to leave that like that. All right, now, so far I've only plugged in numbers, okay? I don't have to only plug in numbers. Maybe I need to make a change of variable. All right, so maybe I want to let x equal w. All right, maybe I need my variable to be w. So then I get f of w equals w squared minus 2w plus 1. All right, now you might be wondering, well, why would I do that? Well, again, it might just be a matter of meaning, right? It may be that W is more descriptive for what you're doing. Maybe it refers to the width of a rectangle, right? So instead of calling it X, you want to call it W. Right? Now you may also have more of a formula, okay? Maybe you're working length and width, and you have length in terms of width, and you have to plug length in. So maybe we have X equals 2W plus 1. All right, so then F becomes F of 2W plus 1, which means I need to replace all of my X's up there with 2W plus 1. So that means 2W plus 1 squared minus 2 times 2W plus 1 plus 1. All right. Now, in order to simplify this, right, I've got some work to do. Right? So I have to multiply this out. So if I multiply 2W plus 1 times 2W plus 1, I'm going to get 4W squared plus 4W plus 1. When I multiply 2W plus 1 by negative 2, I get negative 4W minus 2, and then I have a plus 1 at the end. All right, so you need to expand that and then collect up any like terms you've got. All right, so I've got 4W squared and no other W squareds. I've got a plus 4W and a minus 4W. And then I've got a... Is that how that actually works out? Yeah, it is. I've got plus 1, minus 2 is minus 1, plus 1 is 0. All right, so this would be it right here. Okay. All right, so there's a lot of different ways you can plug stuff into functions. All right. All right, so I talked about the vertical line test already. I talked about finding the domain. Finding the range of, so we talked, this was all under the auspices of the domain of the function. So to find the range of a function, right, the range is basically described by those values that we're allowed to put in, right? So it's the values along the vertical axis, the y-axis, if you're looking at standard function notation. There's no set way of finding the range. Like there's not a formula I can tell you, do this and you will always get the range. All right, you have to have some knowledge about what functions look like, right? You have to have some information about where functions top out or bottom out. We talked about max min in class yesterday. All right, so one way that you can find the range of a function is basically just put it on the calculator, right? That's one thing you can do. Type the function into the calculator and get it. It's a little bit less important to know the range of a function as it is to know the domain. All right. Now, I'm not saying it's not important. I'm just saying on the scale of, 1 to 10, if knowing the domain of a function is 10, knowing the range is like a 9. All right. So it's a little bit below that. It's helpful, certainly, because the range can give you things like the maximum and minimum value of the function. Maybe the function has no maximum value. Maybe it goes to infinity. If we look at this, right, this is a parabola, right? And it's an upward facing parabola. You can tell that by the leading coefficient being positive. So if I come over here to my calculator, and I think I still have stuff in here from yesterday. Yes, I do. All right, let's get rid of the yesterday stuff. If I put this into my calculator, right, x squared minus 2x plus 1, and I don't remember where we left our graphs yesterday, so I'm just going to zoom standard. All right, you can see what I get there. All right, so I get a parabola that is facing upward, meaning it has no maximum value. So the upper limit of this parabola is positive infinity, the upper limit of the range. What's the lower limit? Well, it's hard to tell, right? It's hard to tell from this where the graph is. All right, so if I zoom this in, I'm going to do a box. We talked about box zooms yesterday. All right, so I'm going to do a box zoom here. Hey, let's try that again. That shouldn't have happened. No. Zoom. Box. Okay, that's good. All right, so. All right, let's pull that out. Let's bring it down. That's good. All right, so this looks like it's bottoming out on the x-axis. All right, so if that's the case, then the lower limit of the range is going to be 0. So use your minimum, right? Use your minimum. All right, bound on the left, bound on the right. Go into the middle and hit enter again. And okay, so this actually didn't come up yesterday, so I'm glad it did today. This is basically 0, all right? This is the calculator's version of scientific notation. So 7.56 e negative 12 is 7.56 times 10 to the negative 12th. All right, so a 7 with 11 zeros in front of it is effectively 0. All right, and this here is, again, effectively 1. Now, again, you could have saved yourself all this calculator work if you simply recognize that this is a perfect square, right? This is a perfect square, so it'll factor into x minus 1 squared. All right, in which case you've got your 0 that way. All right, but if you don't recognize it, again, the calculator's a tool. You've got it as a tool. You may as well use it as a tool if you need to. All right, so I can write the domain and range of this function now. Let me move down a little bit. Right? I can write the domain and range of this function. The domain is all real numbers. Right? So I'm going to use interval notation for this because it makes a little more sense to use interval notation for this. Negative infinity to positive infinity, all real numbers. The range we can get from the graph or we can get from the algebra. The lower limit is 0, and that is included. The upper limit is positive infinity. All right, so this is basically saying here that x is, well, we don't include, hang on, let's try that again. That x is between negative infinity and positive infinity, and y, we are including 0, is between 0 and positive infinity. All right, so you can find the domain and range by fiddling around on the calculator. I mean the range rather by fiddling around on the calculator, or fiddling around with the algebra. Okay, either one of those is fine. Knowing the range of a function ahead of time can actually help you do the graph. So again, it's one of those things, it's the chicken and the egg problem, right? Which comes first? Do I want the graph first or do I want to know the range first? And it just depends, okay? We also have functions that can be defined in 2 different pieces or 3 different, in parts. All right, so when we start looking at some applications problems, not all of our applications problems are going to be able to be defined by a single function. All right, and a situation may be something like you're renting a car and you've got a daily rate and you've got, let's say you pay a certain amount per mile for the first 50 miles that you drive the car. And then after that, the rate changes. So you'll have one function that applies to the first 50 miles that you drive the car. And then you'll have another function that applies to driving the car beyond 50 miles. All right? And these are what's called piecewise functions. Right? piecewise functions. Piecewise functions. Okay. And let's look at a piecewise function. So I have an example here. So suppose f of x is defined to be x minus 1 when x is between -3 and 0. So this is for x between -3 inclusive and 0 not inclusive. And then the function's going to equal x squared for x between 0 and 2, inclusive on both sides. All right. So when you think of a piecewise function, you're really thinking of two different functions, right? All right, so I've got one function, which we'll call y equals x minus 1, which is only defined between -3 and 0. And then I have another function, which is y equals x squared, which is only defined between 0 and 2. Okay? So now if I want to graph this, right, I know what y equals x minus 1 looks like, right? That's a linear function. I know what y equals x squared is. That's a quadratic function. All right, so individually, I know what each of these functions look like, right? So if I were to come over here, all right, I'm going to use red for my line, okay? So the line x equals 1 has a y-intercept at -1, right? So down here at -1, we have a y-intercept. And then a slope of 1, so up 1 over 1. So that's going to come over here and it's going to cross at 1. So my line, if I were to draw the entire line, would look like this. Okay. My parabola, make the parabola blue, all right. My parabola is just y equals x squared. So I'm going to use 1, 1 as a point. All right, so that is going to look like this. Now, what happens when I think about the restrictions? All right, well, the line is only defined from -3 to 0. All right, so if I tick out here, here's -3. All right, so I come down and here's -3 on my line, and we're including -3. Here's 0. All right, so here's 0. We're not including 0. So this, black, is the only part of the line I'm interested in. Okay? All the rest of it, don't need. For the parabola, I'm interested in 0 to 2. All right, so 0, here's 0. Now this time we're including 0, and I'll explain why we're including it in one and not the other. And then 2. So at 2, we're going to be up here at 4. All right, well, I'll make it here. All right, so the part that I'm including is again just the black part here. So the actual graph of this function looks like this. All right, so we're out here at -3 and -1. All right, and so we're down here. We've got a straight line. I'm going to move one here with an open circle. And then for the parabola, we've got a closed circle here at 0. And then 1, 2. All right, and then we're going to go up like that. And again, we'll have another closed circle there. So this is the graph of f of x, right? Just those pieces I had outlined over there. All right. Now, why do I have an open circle? Why do I have one of these open at 0? Why can't I have both of these closed? Well, I can't have both of these closed because if both of them were closed, the function wouldn't pass the vertical line test. I would be able to draw a line down the y-axis and there would be two different values of x. Okay? or two different values of y, rather, for one value of x. So I want to make sure that my function does not violate the vertical line test, because then it wouldn't be a function. All right, so anytime I do a piecewise function, I'm always going to have at least one. I could have both of these open. I could simply have 0 as not being defined on the function at all. That would be fine. There's nothing wrong with that. The only thing that would be wrong is if I had both of them closed. All right. So piecewise functions are going to come up. And I'm just looking through to make sure I'm hitting on everything here. Okay. So I talked about that. I talked about that. Okay, let's talk about, we talked about symmetry, right? We talked about symmetry a while back. And we had three different types of symmetry, right? We had x-axis symmetry, y-axis symmetry, and origin symmetry. Well, if we're talking about functions, we're never going to have x-axis symmetry, right? Something can't be symmetric about the x-axis and still be a function, because it would fail the vertical line test. All right, so when we're talking about symmetries for functions, we're only talking about y-axis symmetry and origin symmetry. All right, y-axis symmetry is what's referred to as being an even function. Origin symmetry is what's referred to as being an odd function. All right, so when we talk about symmetries here, we talk about a function being even, right? An even function has y-axis symmetry. Right? An odd function has x-axis. No, has origin symmetry, sorry. Sorry, my brain wandered there for a second. Has origin symmetry. All right, so those are the only two types of symmetry we have when we're dealing with functions. And so this also simplifies our test a bit, right? Because when we had the symmetries before, when we were just looking at equations, we had three different tests. All right, now we have one test with three possible outcomes. All right, one outcome leads to an even function, one outcome leads to an odd function, and then the third outcome just leads to neither one of them. All right, it's possible for a function to not have either symmetry. In fact, most functions will have neither symmetry. Okay, so the test, here's the test. All right, we replace x with negative x. All right, that's the test. Okay, end of story, that's the test. All right, here are the outcomes. So remember, replacing x with negative x in a function means we replace the x in the function notation. So if f of negative x is equal to f of x, then f is even. If f of negative x equals negative f of x, then f is odd. Okay, I'm going to apologize for the humming in the background. My landscapers are here. I do have the window closed, though. And I'm almost finished. All right, I knew I wasn't going to get through all of this today. I'm trying to stick to our 50-minute time period here. So I'm going to stop after this, and then we'll finish up on Thursday. Okay, so even odd. Okay, so let's take a look at, keep doing that. Let's take a look at some functions. Okay, hang on. Let me get some arg. Let me get some functions here. Hang on. It's easier if I can take them out of the book. Domain and range. Come on, even odd. I know you're here. All right, I'm just gonna fudge it. I'm not gonna go. I don't want to waste time on the video doing that. Okay, so let's take a look at y equals x squared minus 7. All right. Actually, I should use f of x, shouldn't I? Let's use f of x. All right, so remember, it's one test with 3 possible outcomes. Okay, so I only do the test one time. This is a point of confusion with some students. Okay, I only do the test one time. And the test is, I go f of negative x. So we've done this enough already, right? Replace every x in the problem with negative x. And then simplify. Okay, so right here, what happens when I take negative x squared? That's negative x times negative x. That's a positive x squared. So that's x squared minus 7. And what is this? Is this the same as the original function? Yes, it is. That is f of x. So that means this is an even function. Okay. If I take, do I want to, yeah, I guess I'll go that way. All right, give me a second. We looked at one yesterday. We looked at one, was it yesterday? I think it was yesterday. Well, let's find out. Oh, but it wasn't exactly. Oh, yes, it was. Okay. Okay. So this is one of the functions we looked at yesterday when we graphed. All right. So let's see what this one does. All right. So if I take f of negative x, again, I'm going to replace every x in the problem with negative x. Okay. All right, that's fine. I'm just noticing what's happening here. All right, so x to the third. Remember, when you raise a negative value to an odd power, it stays negative, right? So that is going to be negative x to the third plus a negative x is just minus x minus 1. Okay. All right, so I have to look now. Is this the same as this? No, it's not. So this function is not even. So now what do I do? Well, to continue the test, once you know it's not even, you have to see if it's odd. So to see if it's odd, you're going to factor out a negative 1. All right, I'm going to factor out a negative 1. And when I do that, that becomes x to the third. That becomes plus x. That becomes plus 1. Okay. All right, so there's that. So now I have to ask, is what's inside the parentheses the same as what I have over here? And it's close, it's very close, but it's not the same. All right, this one has a minus 1, this one has a plus 1. All right, which means this is not equal to negative f of x, right? So this one tells me it's not equal to f of x. This one tells me it's not equal to negative f of x. All right, so this is the third option, right? The function's not even, right? So this not equal to f of x means it's not even. Not equal to negative f of x means it's not odd. All right, so if it's not even or it's not odd, this function is neither. All right, it's neither even nor odd. All right, so let's take a look at, I'm going to do one more of these, and then I'm going to stop. Oop, sorry about that. All right, so let's do f of x equals x to the fifth minus x to the third. Okay. So when I do the test here, f of x equals, f of negative x equals, we replace everything with a negative x. Okay. And I work this out. So negative x to the fifth. Again, odd powers stay negative. So that becomes negative x to the fifth. Odd powers stay negative, so that is negative x to the third, but we're subtracting, so it's minus a negative x to the third, so that becomes plus x to the third. All right, and then I stop. This is my stopping point. Is this the same as the function? No, it's not. All right, so this is not equal to f of x. So I know it's not even. All right, so I continue on. I factor out a negative 1. And when I factor a negative 1 out of this, I get x to the fifth. When I factor a negative 1 out of this, that becomes negative x to the third. All right, and then I stop and ask, is what's inside the parentheses the same as the original function? And now, yes, it is. All right, so because this is the original function times a negative 1, this is negative f of x. All right, which makes this function odd. Okay. All right, so I'm gonna leave it here because this is about how far I would have gotten if we had class today. And again, I apologize for canceling the live stream. So you have some of the homework you'll be able to do. Actually, you might be able to do all of the homework depending on, how well you are at, reading the book and everything. But take a look at the problems in the book, okay? And we will pick up. I have one more topic to cover. All right, but I need more than the 2 or 3 minutes that we have left in our regular class period to do it. So I will pick up with this tomorrow, so make sure you watch the video, and I'll see everybody tomorrow.